Hello. Okay. Good afternoon, everyone, and welcome back to DSP. So let's continue from yesterday's topic, right? So just a bit of recap. We were talking about sampling, right? So in sampling, the equation goes that if we want to create a sequence of numbers from a continuous time signal by taking a look at the signal every once in a while, every once after a period of t, right? So x, now the time index become integers, 变成整数, become integers, and xn equals to x, the continuous function evaluated at n times the sampling period. Okay, so that's a mathematical definition of sampling, right? So if we take let's just draw a very simple sketch. If a function, if a signal in continuous time looks like that, then by sampling, we are going to turn this continuous waveform into spikes, right? Into spikes in this sense. We evaluate the signal at every integer multiple of sampling period t. So let's say t, 2t, and so on, n times t. So that's x of n right there. And t goes in this direction, right? So we're turning a continuous waveform into a sequence of spikes. And each spike has a different height according to the signal value, right? So that's very simple definition. But in the end, we were also interested in how to, we asked a question. So whether this continuous to discrete conversion, whether or not we can go back. If we can go simply from continuous time to discrete time, can we go back, right? And so there's the kind of caution we need to be careful about. So it's a matter about sampling frequency. And the conclusion was that we want the sampling frequency to be sufficiently high, at least 2 times higher than the bandwidth, right? So that's our conclusion from yesterday. So let's take a brief review. So here on this page, you see another way to look at the action of sampling. Okay, so here we claim that our sampling is just like multiplying your signal with this s of t. Okay, so that's like another way to look at what's going on when we sample a signal. So let's explain. So here, that's a more standard definition. Okay, this definition will show up more often, but alternatively, 就是换一种方式来看 alternatively, you can also regard sampling as if we are multiplying our signal. That's this signal, okay? Or multiplying this signal with s of t, and we denote the result as x sampled. Now it's sampled. Yeah. So, but take a look. What is st then? S of t is just a sequence of equally high Dirac delta functions. Okay, so s of t is just an infinite sum of infinitely many delta functions, each shifted at t equals to nt. Right. So now if we just draw a sketch of s of t, very soon you realize it's very simple. It's just a sequence of spikes. Just a sequence of spikes with all equal height, equal unit height of 1. And that's in the continuous time domain. This is s of t. Okay? So simply, so now you can consider what's going to happen when we multiply. Imagine what's going to happen when we multiply. When we multiply the waveform with this sequence of spikes, the result is, of course, now you get also the result. If you just multiply the waveform with s, which is multiply 2 of them, then the result, of course, is going to be a sequence of spikes, but the heights now are adjusted according to the waveform. Right? So that's very simple. You have just all the spikes right there, right there, right there, and so on and so forth. And the time index is still in continuous time, right? I say this is an alternative method to look at what's going on, because here the result is a sequence of numbers, a sequence number. Here, strictly speaking, the results conceptually are still in continuous time. Note that the index is still t, right? But just know we understand that by sampling the important spirit is that we are missing, we are just throwing away anything that's in between samples. That's the spirit of sampling. We ignore, we throw away. We don't. We just what's the word? We dump. Yeah, we trash. We just we are not looking at anything that's in between samples anymore, right? So that's the spirit of sampling. So I say that yeah, by multiplying your waveform with S, that's also another way to look at what's going on in sampling, right? Now with this alternative way of explaining sampling, the cool thing is that now we can talk about spectral effect, spectral, 频谱上面的 effect. Okay? Now we are ready to talk about the spectral effect of sampling. And the secret, the trick is that S of t, even though it's defined as an infinite sequence n delta t minus nt. But if you take a look at this signal, and you really focus on, that now signal is a periodic signal in continuous time. Just like everything in between samples are missing, but like conceptually, the time index is still small t, right? It's still the continuous time index. 那个时间的图标还是 continuous time. Okay, so you just force yourself to think of this as a periodic signal. Why periodic? Because it repeats itself, right? It's just periodic for every, and the period is exactly t. The period is exactly t. It's a periodic signal. Okay, and that's an important way to, the kind of key step to understand this. Right? The key step is to force yourself to think about the sequence spikes as a periodic signal in continuous time. Right? So because it's a periodic signal in continuous time, we know that any such signal you can perform Fourier series expansion. You can express this periodic signal as it's a Fourier expansion, as a summation of now k with a coefficient, a known coefficient for now, but you just expand it as an e to the j k times the frequency, the fundamental frequency. That's 2 pi divided by t. T being its period. Being this a period of this periodic signal. If you force yourself to look at this and say, oh, this is a periodic signal in time, you can do that. You can force yourself to convince yourself you can take a look at the signal this way. Okay? Only by looking at the signal this way, now that you can convince yourself, now maybe we can try to express the signal, which is periodic, by its Fourier series expansion. Okay? Fourier series expansion in general has this form. It becomes a summation of unknown coefficients to be determined, and this is sort of a series, some summation of unknown coefficient times the harmonics. Here the summation index is k. When k is 0, it's DC. When k is 1, it's fundamental frequency. When k is 2, it's second harmonics, and so on and so forth. For any periodic signal, we know we can do this. Okay? So now, if you're with me in this, then it turns out that you can determine AK in the most standard way. Okay? We leave it as a FUD question. Okay? We'll come back to this 2 weeks from now. But just if you're with me, it turns out that all the coefficients right there, if you just perform this direct calculation of the coefficients, you get the coefficients all are equal to, I hope I get this correct. Where is it? Here, yeah. Turned out that all the coefficients are 1 over t constant. Yeah. Okay? So I said this is an important middle step, intermediate step for us to understand the spectral effect of sampling. Okay, that's an important middle step. Right? So far, so good? First series expansion, still in continuous time. Right? But now with this, then we can finally jump, after a few quick steps, if S of t has this first series expression, then when we multiply the two of them, when we sample by multiplying our original waveform with S, turns out that we just copy everything here. S is S, right? S is S. If we just substitute this S with this long expression right there, then we get X of the sampling result is the original waveform times, I'm just going to copy everything right here, summation k, and ak we know, now with some simple algebra, it's going to be 1 over t, all the same, e to the j now k times the fundamental frequency. That's the first series expansion, like that. Okay. So now this is still, everything's still in the time domain. Finally, we are quite ready to get to the frequency domain. Okay. So now let's get to the frequency domain by considering the Fourier transform. Let's say if we take the Fourier transform of on both sides of the equation. Okay. If you take the Fourier transform on both sides, then we found that the Fourier transform of after sampling, the spectrum after sampling will equal to what? Will equal to the Fourier transform of this entire thing. But let me perform a few tricks. So here, to get to that expression over there, we need to rearrange a few terms. First of all, what's going on right there? First of all, maybe this can be moved outside, right? Outside summation, while we move this summation inside. How about that? Just a simple algebra. So now, 1 over t, summation k. Now inside we have xc times every exponential term. Right there. So that's where we are at near the end of the lecture yesterday. And just one step further to complete our derivation. The end result is this. The end result is that since x times this exponential term means modulation, right? So there's a shift theorem in Fourier transform that tells us that when we multiply signal in time by that, then the entire spectrum is going to shift to the right. Frequency increases if k is positive. Okay? But here, of course, k sums over all integer, including the negative ones. So here, also because Fourier transform is linear, we can just all the way move the Fourier transform inside the summation. That doesn't matter. Okay? So 1 over t, now summation k is still there. So that's why we get that final expression. Now the spectrum is going to be shifted by k times 2 pi divided by t. And we sum over all k. So that's an end, kind of a very nice way to show what will happen spectrally when we sample a signal in time. You sample a signal in time in the frequency domain, the spectrum is going to be shifted and they superpose. Okay? They superpose. So that's why yesterday we recommend that it's okay that they will inevitably they superpose, but what we can make sure is that we want this shift. We want to move the t over 2 pi over t. We want to move it far enough away. Because they will be shifted and they will be added on top of one another. We want the shift to be that shift to be large enough. Okay, we want the shift to be large enough so that even if we have a spectrum which is band limited with bandwidth b, and this is in the omega domain, and we know that after sampling, if this is the original xc of j omega, that's origin spectrum, then after sampling, we know that we will get extra copies everywhere. Get an extra copy in the next center around the next frequency, that's omega s, which is defined by 2 pi divided by t. Okay, so we got an extra copy right there. But as long as the sampling frequency, as long as the sampling frequency is greater than 2 times b, then we're fine. Then we're fine because the two copies don't overlap, and we like that. Okay? We're okay with that. Okay with that. And similarly, in the negative frequency part, minus the sampling frequency, we get an extra copy, but as long as omega is greater than 2b, because we know that that's also b, right? If this is b, then that's also b, right? So therefore, if this shift is far enough, we're happy. We want it to be far enough. Okay? So that leads us to the famous Nyquist-Shannon sampling theorem, which recommends that. Basically, it recommends that. Oh, there's a bit of inconsistency. I apologize. I apologize. Sometimes when we say b being the bandwidth, okay, I need to be careful. B being the bandwidth, then it matters which unit we're talking about. Okay, so here on this slide, I say if the sampling period is defined by 1 over t, that's in hertz. T is a time, right? So 1 over t is the unit is hertz. Okay, so let's try to stick to this definition. Okay, where b denotes the bandwidth of a signal in hertz. So if the b is the bandwidth of the signal in hertz, then here we should say in big omega, here the bandwidth should be 2 pi b, and it's radian per second. That's the unit of omega. Let me also mention that. Okay? Because Fourier transform is ej omega t, right? So if we write it this way, omega has a unit, not hertz, but radian per second. And there's a factor of 2 pi. You all know that, right? Yeah, please refresh your memory, okay? After a long winter break. Omega unit is the unit, I suggest, let's write it this way, radian per second, okay? So if b being the bandwidth is in hertz, then on this plot, the bandwidth should be 2 pi b, okay? 2 pi b. But the conclusion is still the same. Now we still want this shift to be far enough so the two copies don't overlap. That conclusion stays the same, right? The conclusion stays the same. The conclusion, our recommendation, or Shannon's recommendation. Shannon-Nyquist recommendation is that we want this shift 2 pi divided by t to be greater than 2 times 2 pi b. 2 pi. So therefore, the conclusion is still the same. So therefore, we want the sampling frequency to be at least 2 times b. Then the shift is far enough. We don't have overlap, and we are happy because there will be no interference there will be no interference between spectral components. Okay. So that's a bit of a recap from yesterday. And here, let me maybe go through the slide quickly to see if we're missing any notes right here. Okay. So I think we are pretty much all right for all the previous slide, but on this particular slide, we have a kind of a note right there. Of course, the suggestion, we were making a sketch, that's that sketch. And we have a suggestion that we want sampling frequency to be greater than 2b. And now I have a remark right down there. All right, let me share with you. If you take a look, there's a historical question that I claim. I claim this question is historical. What if we have a situation of sampling rate being 8,000 hertz, but the bandwidth is about 6,000 hertz? The question is, do we satisfy Shannon's recommendation right here? is sampling frequency greater than 2B? The answer is no, right? 8,000 clearly is not greater than 2 times 6,000, right? So the answer is we have trouble. We would have some trouble. And I say this is historic. Anybody want to guess what's the historical question people were facing sometime back in the 20th century? What's going on when people come? This is a very real scenario. It's a real scenario. Do you still call on phones? Do you use your phone to talk? No, you don't even talk over the phone, right? Or ever in your life when you were little? Yes, yeah, 小时候有. We all talk on the phone at some point of our life, right? So traditionally, the phone, the landline network, was analog, the most early on, very, very early time. But then later, they decided they want to digitalize the landline system. And they decided that the sampling rate was the best they could offer. The sampling rate is 8,000 hertz. That's a landline telephone. Okay, if you just pick up the phone and press on buttons, or even earlier without the phone. So those landline network has been digitalized, but the sampling rate has steadily been 8,000 hertz. But the problem is, landline is supposed to transmit speech signals, right? We talk over the phone, right? And it turns out that our speech signal, if you understand it, our bandwidth is more than half of the sampling rate. Our speech signal contains component easily up to 6,000 hertz. Up to 6,000 hertz. So now we are facing a situation. They were facing a situation. They used to have this situation where the landline system has a sampling rate of 8,000 hertz, but that system is supposed to support speech communication, but we understand that speech has a bandwidth that extends higher than half of the sampling rate. Okay? So that's a kind of a difficult situation they were facing back in old time. So guess what they decided? They decided to. So turns out that they didn't decide to increase the sampling rate, but instead they decided to low pass the speech. Right? So that's why when you talk over the phone or any communication system at 8,000 sampling rate, when you talk over the phone, sometimes it's hard to enunciate numbers or English letters, alphabet, right? A, B, C, D, E, F, G, H, I, J, K, S, and F are particularly hard to distinguish. So next time you can try, okay? Call somebody on the phone and ask them to tell if you're saying S or F. S or F. Over the phone is difficult because S and F both contains components higher than 4,000 hertz. Right? But they decided to low pass the speech first. But if S and F are hard to distinguish, then what should we do? Should we avoid saying S or F? No. Like in communication, they have ways to say like 1, 2, 3, 4, 5, 6, 拐八 go 动, right? That's a strategy. And also in English, A for alpha, right? Alpha for A, B I forgot. C is Charlie. D is Delta. And there's a way to enunciate all the letters, just to make sure that the people you're talking to do not mistake you what you mean when you spell a sequence of letters. Now, so that's a historical question. People really were facing the kind of the inadequate sampling rate. So in the end, they decided they need to low pass. It's better to low pass than to have alias. Okay, so that's their decision, and. So what's next? So here, now finally, let's take a look at the theorem, the famous Nyquist-Shannon sampling theorem. Okay, and so it states that suppose that we have a signal, we take the Fourier transform, we have a spectrum, and suppose that the spectrum is band limited with you can find a upper bound for the frequency such that the spectral components are all zero for any frequency beyond that limit. Okay, so the conclusion that then it's okay if we sample with a frequency that's at least 2 times that limit. Okay, if you sample with a sampling rate that's 2 times high, at least 2 times higher than the bandwidth, you're fine. In what sense? You're fine in that now we can get back the waveform. XC can be uniquely determined by its samples. You can go back from discrete time to continuous time. Okay? And that determination can become unique. Okay? Now, so I have a few remarks right here. Okay, so far so good. I have a few final remarks before we end the first lecture 1. Okay, first remark. In this course, we usually assume our signal is real valued. Okay? Usually, unless otherwise mentioned. Okay? Usually we assume that X is real. But then, if we agree that the signals are real, then consequently, when we look at the spectrum, we have this some symmetry in Fourier transform. Okay, so let me maybe tell you a few more things about Fourier transform. Turns out that if the signal is real, then when you take the Fourier transform, the spectrum evaluated at the negative frequency should be, if I remember correctly, should be the spectrum with complex conjugate. Okay, that's a symmetry. Okay, so that can also be easily verified using the definition of Fourier transform. Okay, Fourier transform has both sides, right? But if your signal is real, then after Fourier transform, when we go to the negative frequency, when we flip the spectrum, there should be a complex conjugate relation. Complex conjugate, 这是共轭复数 complex conjugate. That's the notation we're going to be using for complex conjugate. That's a simple matter of fact, right? And by now you should recall that Fourier transform is in complex domain. It's a complex number, real part, imaginary part. Okay, that's why we talk about complex conjugate. But now then we have a slight problem. When we draw a sketch like that, often we need to remind ourselves that this is not entirely correct because whenever we're drawing the imaginary axis, the imaginary part, right? So strictly speaking, I should either tell you that this is after take the absolute value right here. Because the spectrum, the Fourier transform has both the real and the imaginary part in general. Real in time, but after Fourier transform, there's going to be the imaginary part jumps out. Okay? So when we draw a sketch, it's really a sketch. It's really like drawing a cartoon. 画卡通, 画漫画而已. It's really like just a sketch, just an illustration of an idea. Illustration, in this case, the illustration of the idea that when we want the sampling rate to be high enough. Okay? For that purpose, it's fine. Okay? Just to explain the idea of sampling. But please be reminded from time to time that Fourier transform is complex valued. Okay? And we have this symmetry, but fortunately, when we take the absolute value on both sides, then what do we get? Because complex conjugate has the same magnitude, right? Complex conjugate preserves the magnitude. Therefore, just so we say x equal to right there. Yeah. So this is something for us to keep quite kind of relieving, 好险, relieving that, there's a reason why when we draw a spectrum, we always use a symmetric shape. In this case, a triangle with equal sides. Okay? We use a symmetric shape. We don't say, oh, we have a spectrum, and the spectrum looks like Yeah, oh, we don't do that. If some people do that, then that's fine. Their signal is complex valued in the time domain. But when we stick to this convention that most of the time we talk about real value signal in time, therefore when you draw a spectrum, when you draw the magnitude spectrum. Oh, by the way, taking absolute value means has a name. So this is called magnitude spectrum. So a bit of a definition of terminology, magnitude spectrum. That means we take the absolute value, the shape is going to be symmetric just because our signal is assumed to be real. Okay? So that's kind of convention right here. Convention right here. Yeah. And now I have a third comment or remark down there, which I'll just say it. So it's kind of interesting that when you take a look of sampling theorem, we assume that if our signal it has a finite bandwidth, right? If your signal has a finite bandwidth, then sampling at sufficiently high sampling rate, 2 times higher, you'll be fine. But it turns out that I have an interesting note right there. A somewhat subtle, interesting point to make. Turns out that mathematically, any band-limited signal cannot also be time-limited. Okay? A signal cannot be both finite in frequency and finite in time. Any band-limited signal has to extend infinitely in time. We say from the dinosaur time to forever. Mathematically, that means something for you. But you don't have the time of the universe. Any signal, we have a lifespan of 80 years or 90 years. Right? So mathematically, this is a kind of subtle point to consider. Turns out that any time-limited signal cannot also be band-limited. So if you take this seriously, then we have trouble. Then you have trouble, right? We talk about band-limited signal can be sampled sufficiently, but no signal is band-limited. That is to say, something for you to ponder upon. Okay, during the long weekend. All right. So with that, that's probably the end of first lecture. Hope you're still with me so far. Any question or comment? So let me ask you a question. Maybe some of you have heard it. So now we take the absolute value and call it magnitude spectrum. How about, but then still the spectrum is complex valued, right? So what's missing? What's missing? If we just consider magnitude, we just draw the magnitude, what is missing? The phase is missing, right? So let me just take the chance to also introduce to you the definition of phase. Okay? The phase of a spectrum, thank you, is defined as, is denoted as by an angle, right? The angle of your spectrum is defined by, if I remember correctly, arctangent of the imaginary part divided by the real part. Okay, that's a phase spectrum. So with magnitude and phase, with both of them, now you can completely characterize, completely define your spectrum. Okay, so this is called the phase spectrum. Okay, all right, so that will be end of lecture note number 1. So let's take a 1-minute break while I'm switching. 好，休息10分钟，7th inning， 7局。休息10分，I say one minute, right? Sorry. 1 minute. 10 minutes, then we are almost done. It's nice we have a long weekend after 4 struggling days. Have you all been able to select courses smoothly? 选课顺利吗？ Or is this a too sensitive question to ask? All right. Oh, by the way, we announced homework number 1, right? Did we? Oh, yeah. So we will announce, unfortunately, before your break, we will announce homework number 1, which has 2 written problems, as well as 1 computer part. The computer part will require you to install MATLAB or have access to MATLAB. So please, if you don't have MATLAB on your computer or you don't have access to MATLAB yet, please plan ahead, okay? Do it sooner rather than later. So, and in case of difficulty, please talk to your TA, how to find MATLAB. I think NTHU has a subscription for university-wide licensing. Okay, so everybody should be able to download it from our system, from our information system. Okay, so yeah, welcome back to DSP. Welcome back to DSP. Now we are in the second lecture already. In this lecture, we are going to go through some selected properties of discrete time Fourier transform, okay? Or DTFT, a version of Fourier transform for discrete time. Therefore, the name DTFT. Okay? It's some kind of Fourier transform specifically for discrete time signals. So here comes the definition. The definition is for any sequence x of n, we define this as its Fourier transform. Okay? For any sequence x of n, now we have a definition. So the definition goes that we are going to multiply our signal with this complex exponential part of e to the minus j omega n, and sum over all n. Okay, n from minus infinity to infinity. And the result goes from time domain to frequency domain. Okay, the result is going to be a function of omega. The result is going to be a function of omega. Yeah? And the notation is somewhat special. Okay, still we keep using the capital letter for spectrums. Okay? That's for sure. But inside, please bear with me so far. Inside, let's use the textbook notation. Inside, this is spectrum, but somehow there's a reason, which will be clearer later, okay? There's a reason why the textbook insists that we put e to the j omega inside right here. But the key idea is to go from time domain n to frequency domain small omega, okay? So the result is the spectrum with capital letter X, okay? So that's a kind of mathematical straightforward definition. And so let me read the remarks first, okay? So now there is a question regarding the unit, okay? The omega, now small omega right here in this textbook has a unit which I recommend that to think of the unit as radian per sample. Radian per sample. Why? Because omega tells you how much phase is increased when you jump from sample to one sample to the next. Okay? High frequency, you have more phase jump. Low frequency, smaller jump. But now, therefore, the unit of frequency now, as I recommend, should be radian per sample. Okay? Radian per sample. Now, so that's the first thing. And now, just to reiterate that x of n, the signal is discrete time, and its outcome, please think of it as an outcome of sampling a continuous time signal, right? For sure. And now with a non-specified sampling period t, okay? Sampling period t. No, the unit t. So let's talk about unit. Omega has a unit of radian per sample, and x may be the result. Still, think of it as a result of sampling a continuous time signal at n times t. Where t, now t has a unit of, if you will, second. Okay, t is time. T is really a length of time. Let's say the unit is second. What's more? What do we have right here? Okay, so now the third sentence right there is pretty important too. So I want us to really understand this. So now we have this kind of confusing. We have a small omega, and we have just to compare. We also have the good old Fourier transform in for continuous time. That is, the continuous time Fourier transform goes this way, right, with big omega and integral. So there's a big omega for continuous time Fourier transform, a small omega for discrete time Fourier transform. Okay? So I want to just jump to the kind of the result that is correct. So please remember this relation. Okay? The relation between small and big omega in this context, in the context of sampling, the relation between small and big omega is this. Okay? Small omega right here. Small omega correspond to t times big omega. Okay? And we say big omega's unit is radian per second, as we previously disclosed, right? I previously just mentioned this. And here our unit is radian per sample. Because the unit t, what is t? T is the sampling period, right? T tells you how many samples, how many seconds per sample. That's the meaning of sampling period. So it really makes sense, right? Small omega, radian per sample. Big T, how many seconds per sample? That's the sampling period. It's the length, right? And big omega's unit is radian per second. So everything is consistent, okay? Please bear in mind this is correct, okay? Just bear in mind it's very simple, it's correct. Yeah. So here's a very simple exercise. Right? Let's try to take a look, okay? So here's a simple exercise. If our sampling rate right here is 40k kilohertz, no, 58k, so let's say if f equals to 1 over t equals to 48 kilohertz. That's the specification. Audio sampling. If sampling rate is 48k, which frequency in hertz does small omega pi divided by 6, what does that represent? What does that value represent? Okay, please work on this for a minute, okay? To see if you can get this very simple idea. Okay, very simple idea. If sampling rate is 48k hertz, then what frequency in hertz does that 6 pi over 6 represent? What does it correspond to? So if you will take some time to work it out, okay, using this very simple relation. Okay, using this very simple relation. Anybody has an answer already? 4k hertz. Yeah. Okay. So thank you for the 4k hertz answer. That is correct. So let's work it out. If sampling rate, oh, by the way, sampling rate usually is denoted as f sub s. Okay, f sub s is 48 kilohertz, and t is, so omega equals to pi divided by 6, right? Equals to t big omega, which is, what is t? T is 1 over sampling rate, okay? 1 over 48k hertz, that's t, times this omega that we don't know yet, right? So therefore, big omega is what? Big omega is pi divided by 6 times 48k hertz, right? That equals to what? 8 pi. 8 pi radian per second. That you say. 8 pi, oh, 8, that's weird. 8,000 pi, 8,000 pi radian per second. But this is the frequency, angular frequency, if you will. angular, so we are saying that small omega of pi divided by 6 corresponds to an angular frequency of 8,000 pi radian per second. So if you want to convert this back to hertz, you still need to divide by what? Divide by 2 pi to get back to the hertz unit. Okay? So therefore, this frequency is 8,000 pi divided by 2 pi, so that's 4,000 hertz. Okay? So that's a simple exercise. You'll encounter again and again and again. Okay, that's why during this very first week, I want to introduce it. Okay, just please just refer back to this very simple relation. Okay, and you are going to be good. Yeah. All right, so that's a simple small exercise. But now we can show that with that new definition of Fourier transform, we have the inverse Fourier transform that can be defined in that way. The inverse DTFT. The inverse FF DTFT now has a sort of a similar expression. Okay, so let's take a look. The inverse Fourier transform has a similar expression in that we now, of course, we're going back from frequency to time domain, right? First thing first. But what do we see here? In here, we are multiplying the spectrum with same thing, same factor, e to the j omega n with a plus sign, okay? Not minus anymore, with a plus sign. But then the idea is when we go to the time domain, when we go back to the time domain, we are actually essentially collecting every component, okay? We're collecting every component in the frequency domain. And by collection, we mean that we are taking the integral because this is continuous with respect to omega. Okay? But by doing this integral, we are collecting everything. We have the magnitude and phase embedded in this expression. Right here is a representation. So by multiplying it with this wavelet, if you will, with all the small components and take the integral for collection, for collecting everything, and then you go back to the time domain. Okay? And there's a factor of 1 over 2 pi right there that needs to be there, and we'll show that. Okay? So, but conceptually, this is the way I look at inverse Fourier transform. It's a matter of collection. 把一些东西收集起来. It's a matter of collection, collecting all the free components and go back to the time domain with a normalization factor of 1 over 2 pi. So let's take a look. This can be easily verified. Okay? So how do we verify? Now, if x has been defined as summation of x of n e to the minus j omega n. Okay? But for my derivation, I got better be careful. I changed the dummy variable to m. Okay? And you'll see in a moment why this is better to denote the dummy variable by another letter, choosing another variable. So if this is the definition of DTFT, now when we just evaluate this integral, so in this integral, we're going to go from minus pi to pi and take this times e to the j omega n d omega. So we just substitute this term with that expression. That's what we are going to do, okay? We're going to substitute this term with that summation, okay? So when we do that, we have the substitution of summation m, xm, e to the minus j omega n times e to the j omega n, and the integral goes with d omega. Just a simple substitution. So what comes next? So just the trick that whenever we see summation and integral, such kind of thing, try to change the order. Okay? Try to change the order. Most of the time, you're going to be okay. If you change the order, then now summation over m, integral goes inside. Okay? So let's see what this this is good, how good this is. E to the minus j. Now I'm going to say minus j omega, the the difference. Now we have a term m minus n omega d omega, right? And further, when we change the order, now this term, what can we do for this term? This term does not depend on omega, right? So you can go outside the integral. So the next step is to make it go outside. And now inside the integral, everything now is simplified. We have e to the minus j. Actually, I don't, minus j m minus n omega d omega, right? And this term can be very simply evaluated, okay? What is e to the j something? It's a periodic signal, okay? And m and n are both integers. Let me emphasize, m and n are both integers. M and n are both integers. Therefore, when you evaluate this integral, it's going to be, notice that this thing equals to 0 when m does not equal to n, right? And it equals to what? The thing inside here equals to 1 when m equals to n. And if you take an integral of 1 within this interval, the length of interval 2 pi. So let me just jump to the conclusion. It equals to 2 pi when m is equal to n. Yeah? So now, finally, okay, if you're with me so far, finally, summation of something times an integral that's almost always 0 unless m equals to n. So this summation leaves us with only one term. The only non-zero term. There's only one non-zero term in this summation. The only one non-zero term in this summation becomes 2 pi times x of n. And that finishes our derivation. Okay? And that finishes our derivation. So that's kind of the standard trick when you see the summation integral, change the order. Right? So we're running out of time. Thank you for being here with me today. And have a nice long weekend. We'll see each other on next Wednesday. Thank you.